Everything we thought we knew about the cosmos has been wrong. Over and over, our deepest beliefs about space have been shattered by a handful of stunning revelations. We will explore 25 specific space discoveries that fundamentally rewired our perception of reality itself. By the end, you will see the universe in a completely new way. What invisible force is tearing space apart? And why did we not see it coming? Which cosmic break, through most challenges your view of existence, our entire cosmic history, began with a single, violent event we now call the Big Bang. For centuries, the idea of a static, eternal universe was the dominant belief, a comforting notion of a cosmos that was simply always there. But that belief was shattered in the 1960s by two radio astronomers who were not even looking for it. Arno Penzias and Robert Wilson were working with a massive, ultra-sensitive horn antenna in New Jersey, trying to clean up radio signals for satellite communication. Yet no matter what they did, a persistent, faint hiss plagued their equipment. They checked for every possible source of interference, even famously cleaning out pigeon droppings from the antenna, convinced it was some kind of earthly nuisance. But the hiss remained, a constant, uniform whisper coming from every direction in the sky. They had accidentally stumbled upon the oldest light in the universe, the cosmic microwave background radiation. This faint afterglow is the cooled remnant of the universe's hot, dense birth. The echo of the initial explosion stretched and faded over more than 13 billion years. This was the first solid, tangible evidence that the universe was not static, but had a definite, explosive beginning. It confirmed a stunning prediction of the Big Bang Theory, fundamentally changing our origin story. We were no longer inhabitants of an unchanging, infinite cosmos, but of a dynamic, expanding universe with a clear starting point. This single discovery rewired our entire understanding of existence, forcing us to confront the profound question of what, or who, could have set such a magnificent chain of events into motion. That faint cosmic whisper was not the only clue pointing to a dynamic universe. Just a few decades earlier, another discovery had already begun to pull at the threads of a static cosmos, and it came from an astronomer staring at strange, swirling nebulae. Edwin Hubble was using the most powerful telescope of his time at Mount Wilson Observatory, peering into the depths of space. He was studying these fuzzy patches of light, which many assumed were simple clouds of gas within our own Milky Way. But Hubble made a breathtaking realization. He confirmed that these nebulae were not clouds at all. They were entire galaxies, vast islands of stars, far beyond our own. Our universe was suddenly, and shockingly, much larger than we had ever dreamed. But Hubble did not stop there. By analyzing the light from these galaxies, he noticed something even more bizarre. The light was shifted toward the red end of the spectrum. This redshift meant that these galaxies were all racing away from us. The farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, painted a startling picture. The entire universe, the very fabric of space itself, was stretching. It was expanding. This was not a minor adjustment to our cosmic model. It was a complete revolution. The comfortable, eternal, and unchanging universe of the past was gone, replaced by a dynamic, evolving entity. If you could run the film of the universe backward, all that expanding space would contract, drawing every galaxy closer and closer until they merged into a single, unimaginably dense point. Hubble's discovery provided the crucial, observable foundation for the Big Bang Theory. It showed us that space is not a static stage, but an active participant in the cosmic drama, carrying galaxies along as it grows. This single idea forces us to confront a reality where the universe had a beginning and perhaps will have an end. Yet this expanding universe held another, even deeper secret. The very gravity that should have been slowing the cosmic expansion was not acting alone. In the 1930s, a brilliant and often contentious astronomer named Fritz Zwicky was studying a giant swarm of galaxies known as the Coma Cluster. He calculated how much gravity it would take to keep these galaxies bound together, moving at their observed speeds. When he compared this needed gravity to the amount provided by all the visible stars and gas, the numbers did not add up. The cluster had nearly 400 times more gravity than the visible matter could possibly account for. Zwicky proposed the existence of what he called Dunkel Materie, or dark matter, an invisible substance providing the missing gravitational glue. For decades, his idea was largely dismissed. Then, in the 1970s, astronomer Vera Rubin provided the definitive proof. She was meticulously measuring how fast stars orbit the centers of spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, farther from the central mass, should orbit much more slowly, just as Pluto moves more sluggishly around the Sun than Mercury does. But Rubin found something astonishing. The stars on the galactic outskirts were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within an enormous, invisible sphere of matter, a halo whose gravity was whipping the outer stars around at impossible speeds. The only explanation was that a vast amount of unseen matter was there, exerting its gravitational pull. This dark matter does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. We only know it exists because of its profound gravitational influence. We now know this shadowy substance makes up about 27% of the entire universe, while the ordinary matter that makes up stars, planets, and us constitutes less than 5%. This means everything we have ever seen and touched is nothing more than a minor contaminant in a cosmos dominated by a ghostly presence we cannot see. What is this mysterious stuff, and why does it refuse to interact with the world we know? But if dark matter's gravity pulls the universe together, a far stranger force is actively tearing it apart. For most of the 20th century, astronomers assumed the expansion of the universe was gradually slowing down, as the collective gravity of all matter worked against the initial momentum of the Big Bang. The great cosmic question was whether that slowdown would eventually lead to a big crunch or a slow, cold fade. Then, in 1998, two independent teams of researchers made a discovery so shocking it overturned this foundational assumption. They were measuring the distances to extremely far-off supernovae, using these exploding stars as cosmic mile markers to gauge how much the universe's expansion had slowed over billions of years. What they found was the exact opposite. The most distant supernovae were fainter than expected, meaning they were farther away than any model predicted. The expansion of the universe was not slowing down at all. It was speeding up. This was like tossing a ball into the air and watching it not only fail to fall back down, but shoot away from you faster and faster in the sky. The conclusion was inescapable. Some unknown repulsive force, a kind of anti-gravity, must be at work, overwhelming the pull of all the universe's matter. This mysterious agent was given a name, dark energy. We now calculate that this enigmatic force makes up about 68% of the entire cosmos. Think of the universe as a pie. The slice that is all the stars, planets, and galaxies we can see is a mere 5%. Dark matter is a much larger slice of 27%. But the rest, the overwhelming majority of everything that exists, is this dark energy, a force woven into the very fabric of empty space itself. It is the dominant component of reality, and we have almost no idea what it is. This discovery completely rewrote our models for the ultimate fate of the cosmos. Instead of a grand collapse or a gradual coasting, we now face a future of runaway expansion, where galaxies beyond our own local group will eventually be pushed away so fast their light can never reach us, leaving a dark, isolated sky for any future civilization. The greatest mystery in physics is no longer what holds the universe together, but what is relentlessly and invisibly driving it apart. This runaway expansion driven by dark energy has a startling parallel in the universe's very first moments. The Big Bang model, supported by that cosmic whisper and Hubble's expanding space, was a triumph, yet it left astronomers with some deeply puzzling questions. Why does the universe look so remarkably similar in all directions, a state known as homogeneity? And what caused space to be so incredibly flat, meaning the fabric of the universe lacks any large-scale curvature? The original theory had no good answers. Then, in the 1980s, physicist Alan Guth proposed a breathtaking solution, a concept he called cosmic inflation. He suggested that in the first fleeting fractions of a second after its birth, the universe underwent a period of exponentially faster than light expansion. We are not talking about the steady, gradual expansion we see today. This was a violent, explosive stretching of space itself, a growth spurt of unimaginable proportions. In less time than it takes to blink, a region of space trillions of times smaller than a single proton was inflated to a size larger than our entire observable universe. This idea solves the cosmic puzzles elegantly. Think of blowing up a balloon. A tiny patch on its surface, when inflated, becomes a much larger, smoother, and flatter area. Inflation did the same for the cosmos. It took a tiny, uniform patch of the primordial universe and stretched it into the vast, smooth, and flat cosmos we observe today. It also explains why the cosmic microwave background radiation has such minute temperature variations. These tiny fluctuations are the quantum seeds, stretched to cosmic proportions by inflation, that would later, under the pull of gravity, grow into all the galaxies, stars, and planets we see. Without this initial, frantic burst of growth, the universe as we know it simply would not exist. We would not be here to ponder it. This theory reshapes our origin story once more, suggesting that everything we can see was once crammed into a space so small it defies all human intuition, and that the largest structures in existence were born from the tiniest possible quantum whispers. For centuries, our solar system was the only one we knew. We gazed at the stars and wondered if other worlds circled them, but we had no proof. Then, in 1995, everything changed. Two Swiss astronomers, Mitchell Mayer and Didier Queloz, announced a discovery that would shatter our cosmic isolation. They had found a planet orbiting a star called 51 Pegasi, a sun not so different from our own. This world, named 51 Pegasi b, was the first confirmed exoplanet ever found around a main sequence star. But this planet was nothing like anything in our own solar system. It was a gas giant like Jupiter, but it was orbiting impossibly close to its star, completing a full orbit in just 4 days. This was a blistering, fiery world that defied all our models of how planetary systems form. We called such planets hot Jupiters, and their existence meant our solar system was not the template for the universe. It was just one possible configuration among countless others. This single discovery opened the floodgates. Almost overnight, a new field of astronomy, exoplanetology, was born. Astronomers developed new techniques, like the transit method, where they watch for the tiny dip in a star's light as a planet passes in front of it. Space telescopes like Kepler were launched, staring at vast fields of stars to catch these fleeting shadows. The results have been staggering. We now know of thousands of exoplanets, with estimates suggesting there are more planets in our galaxy than there are stars. Planets are not the exception, they are the cosmic rule. This fundamental shift forces us to reconsider our place in the cosmos. Our solar system, with its rocky inner planets and gaseous outer giants, is not special. It is one of billions, and if planets are this common, then the ingredients for life, and life itself, might be common too. The discovery of 51 Pegasi b did more than just add a new world to our charts. It transformed the galaxy from a collection of distant points of light into a potential archipelago of worlds, each one a new possibility in the great, unfolding story of the universe. The hunt for these alien worlds revealed a cosmos teeming with planets, but it also highlighted a fundamental limitation of our vision. For all of human history, we have explored the universe with just one sense, sight, by collecting the light, radio waves, and X-rays that travel across the void. But in 2015, we gained an entirely new sense. We learned to listen to the cosmos. On September 14th of that year, a pair of colossal laser instruments in the United States, known as the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected something extraordinary. They measured an almost imperceptible shudder in the fabric of reality itself. For a fleeting 20th of a second, the space within the 4-kilometer-long arms of the detectors stretched and squeezed by a distance tinier than the width of a single proton. This minuscule wobble was the first direct detection of a gravitational wave. A century earlier, Albert Einstein had predicted these ripples in his theory of general relativity. He envisioned gravity not as a force, but as a warping of spacetime by mass and energy. When massive objects accelerate, they should send out ripples through this cosmic fabric, like a boat creating waves on a still pond. But Einstein himself doubted we would ever be able to measure such a faint signal. The event that LIGO heard was the collision of two black holes, each about 30 times the mass of our Sun, located 1.3 billion light-years away. As these unimaginably dense objects spiraled toward each other, they churned the spacetime around them, sending out a crescendo of ripples that traveled for over 1 billion years before reaching Earth. The signal LIGO captured was the final frantic orbits and the moment of merger, a cataclysm that converted a mass 3 times that of our Sun directly into pure energy in the form of gravitational waves. This was not just a confirmation of Einstein's genius. It was the birth of an entirely new field, gravitational wave astronomy. We are no longer just stargazers. We have become cosmic listeners. We can now hear the universe, perceiving events that are completely dark to traditional telescopes. The violent dances of black holes and neutron stars that emit no light at all. This new sense allows us to study the most extreme phenomena in the cosmos, revealing a universe that is not silent, but is constantly ringing with the echoes of its most violent and secret histories. That faint, persistent hiss discovered by Penzias and Wilson was far more than just background noise. It was a time capsule, a direct message from the infancy of everything. This cosmic microwave background radiation is the oldest light we can ever see, a cooled and faded relic of the universe's fiery birth. When it was first released, the universe was a searing hot plasma, a dense fog of particles and energy where light could not travel freely. After about 380,000 years, the cosmos had expanded and cooled just enough for atoms to form. allowing light to finally break free and travel across the universe. That first flash of light, once blindingly brilliant, has been stretched by the expanding universe over billions of years into the faint microwave whisper we detect today. It is the universe's first baby picture, but the true revolution came when we looked at this picture with greater precision. Early measurements showed it was remarkably uniform, the same temperature in every direction to an astonishing degree. This was the great horizon problem. How could regions of the universe on opposite sides of the sky, which could never have been in contact with each other, have the exact same temperature? The theory of cosmic inflation provided the answer, suggesting a rapid stretching smoothed everything out. Yet, perfection would have been a problem. A perfectly smooth universe would have remained a featureless cloud of gas. The cosmos needed seeds, tiny imperfections, to create the grand structures we see today. In the 1990s, the COBE satellite gave us our first clear look at these seeds. It revealed that the cosmic microwave background is not perfectly uniform. It is imprinted with tiny variations in temperature, tiny bumps and dips, differences of just 1 part in 100,000. These are the fossilized ripples from the universe's quantum origins, the gravitational blueprints for everything to come. Slightly denser regions, seen as slightly cooler spots in the microwave sky, would pull in more matter through gravity over cosmic time. These overdensities grew, collapsing into the vast cosmic web of galaxies, clusters, and superclusters. Every galaxy, every star, every planet owes its existence to these minute fluctuations in the ancient light. Later missions, like the Planck satellite, mapped this afterglow with even more exquisite detail. By measuring the precise patterns of these hot and cold spots, cosmologists could read the universe's vital statistics like a cosmic barcode. They could determine the universe's age with incredible accuracy, 13.8 billion years. They could confirm its geometry is flat, and they could calculate its precise composition, the exact amounts of ordinary matter, and dark energy. This faint glow is more than a remnant. It is the ultimate origin story, a snapshot of the moment the universe became transparent. Its faint whispers telling us not only how it all began, but what it would one day become. Those fossilized ripples in the ancient light gave birth to the grand structures of the cosmos. But some of those structures would become the most terrifying and enigmatic objects in existence. The journey to accepting black holes was a slow and reluctant one, a battle against the limits of our own intuition. The concept first emerged from the equations of Einstein's general relativity, not from Einstein himself, but from a German physicist named Karl Schwarzschild. While serving on the Russian front during World War I, Schwarzschild found an exact solution to Einstein's complex equations, describing the gravity around a single, point-like mass. His math revealed a boundary of no return, a spherical surface where the escape velocity would equal the speed of light. Nothing, not even light itself, could break free from such a point. Einstein praised the mathematical brilliance, but dismissed the physical reality, convinced that nature would somehow prevent such a monstrous singularity from forming. For decades, black holes remained a mathematical curiosity, a seeming flaw in an otherwise beautiful theory. Then, in 1939, a team led by J. Robert Oppenheimer, who would later lead the Manhattan Project, published a paper that made these objects terrifyingly plausible. They calculated that when a massive star exhausts its nuclear fuel, there is no force left to counter its own immense gravity. The star's core collapses catastrophically, crushing itself into an infinitely dense point. sealing itself off from the rest of the universe behind that invisible boundary, the event horizon. The scientific community largely ignored or rejected the idea. How could something just disappear from the universe, leaving behind only a gravitational ghost? Proof would require not just indirect evidence, but a direct, monumental effort. For years, the evidence was circumstantial but compelling. We saw stars whipping around invisible companions at incredible speeds. We detected intense X-rays from gas, ripped from a normal star and spiraling into an unseen, dense object, heating to millions of degrees before vanishing. But the ultimate confirmation came on April 10, 2019. The Event Horizon Telescope, a global network of radio observatories working in unison to create a virtual telescope the size of Earth itself, revealed the first ever direct image of a black hole. The target was a supermassive giant at the heart of the galaxy Messier 87, weighing in at 6.5 billion times the mass of our Sun. The image showed exactly what theory had predicted: a dark shadow encircled by a brilliant, lopsided ring of light. That dark central shadow is not the event horizon itself, but the point where light is swallowed forever. The bright ring is superheated gas, bent by the black hole's incredible gravity into a perfect circle, a photon sphere that shows us the very last orbit that light can make before it, too, is consumed. This image was not a photograph in any normal sense. It was a picture of a prediction, a visualization of nothingness itself, made possible by the glow of trapped light. It forced us to confront the most extreme consequences of Einstein's theory, places where space and time are so warped that the rules of physics, as we know them, break down. Black holes are no longer science fiction. They are a stunning, observable reality, the ultimate in points of gravity, and the most perfect manifestations of the warped nature of spacetime itself. The shadow of a black hole is the ultimate silence, but the universe also speaks in ticks and beeps of astonishing precision. In 1967, a young Cambridge graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope she had helped build. She noticed a faint, peculiar signal, a series of sharp, rhythmic pulses arriving every 1.337 seconds with the regularity of a cosmic metronome. The signal was so perfectly timed that she and her colleagues half-jokingly labeled it LGM-1, for little green men, wondering if they had stumbled upon a beacon from an advanced civilization. But the truth was far stranger. Jocelyn Bell Burnell had discovered the first pulsar, a celestial object that was both entirely new and a stunning confirmation of a decades-old prediction. A pulsar is a rapidly spinning neutron star, the collapsed, ultra-dense core of a massive star that went supernova, but was not quite massive enough to form a black hole. This stellar corpse packs more than the mass of our Sun into a sphere only about the size of a city. It spins at a dizzying rate, and as it spins, it sweeps beams of intense radiation out into space, like a lighthouse on a cosmic scale. Each time that beam flashes across our line of sight, we detect a pulse. This discovery provided the first direct evidence that neutron stars were real. It revealed the existence of matter crushed to an unimaginable density, where a single sugar cube worth of material would weigh billions of tons on Earth. This created a new, natural laboratory for testing the laws of physics under the most extreme conditions imaginable. The intense gravity and magnetic fields of a pulsar push matter into states we could never replicate on our planet. But the profound utility of these objects lies in their incredible regularity. Pulsars are the universe's most accurate clocks. Their spin is so stable that it can rival atomic clocks in precision. This has opened up remarkable possibilities. Scientists have used arrays of pulsars as a galaxy-spanning navigation system, a potential GPS for future interstellar travel. By monitoring the subtle changes in the arrival times of pulses from many pulsars, we are attempting to detect the faint background hum of gravitational waves from supermassive black holes merging across the cosmos. These cosmic lighthouses, born from stellar death, now guide our exploration of the deepest fundamentals of reality, from the nature of gravity itself to the very fabric of spacetime. The universe's most accurate clocks tick away in the darkness, but to truly grasp the scale of the cosmos they inhabit, we needed to look into the void itself. In December 1995, astronomers pointed the Hubble Space Telescope at a patch of sky near the Big Dipper that was, by all previous accounts, utterly empty. It was a tiny, insignificant point, equivalent to holding a grain of sand at arm's length against the blackness of the night. For 10 consecutive days, Hubble's sensitive eye remained locked on this single dark target, collecting every faint photon of light that arrived. It was a tremendous gamble, a massive investment of the telescope's precious time to stare at what most assumed was nothing. When the data was processed, the result was not a dark, empty frame. It was a universe transformed. That single image, the Hubble Deep Field, revealed a breathtaking spectacle. The blank sky was filled with a carpet of light, a legion of nearly 300 galaxies, each a swirling island of billions of stars. They were not all the same. Some were majestic spirals, familiar and close. Others were mere smudges of red, faint and mysterious. The profound revelation was in that color. The red smudges were infant galaxies, their light stretched by the expansion of the universe over billions of years, finally reaching us as a cosmic fossil record. By staring into this tiny keyhole, Hubble had provided a direct core sample of the cosmos, a look back through time itself. We were not just seeing space, we were seeing history. The closest galaxies in that image were as they were a few billion years ago. The faintest, reddest smudges were from a time when the universe was young, just a fraction of its current age. This single photograph did more than just add new galaxies to our catalog. It provided irrefutable visual proof that the universe is uniformly filled with galaxies as far as our telescopes can see. It confirmed that if you point a powerful enough telescope at any dark patch of sky, you will find the same incredible density of worlds. The emptiness of space is an illusion. The cosmos is crammed with structure, a vast web of galaxies stretching back to near the dawn of time. This single image fundamentally recalibrated our sense of place. It told us that our entire Milky Way, with its hundreds of billions of stars, is just one tiny stitch in an infinite cosmic tapestry, a single voice in a chorus of trillions. While Jocelyn Bell Burnell was listening to the steady ticks of pulsars, other astronomers were wrestling with a far more violent and puzzling signal. In the early 1960s, radio telescopes began picking up intense, point-like sources of energy that had no visible counterpart. They were called quasi-stellar radio sources, or quasars for short. When astronomers finally managed to pinpoint their locations using optical telescopes, they found what looked like faint, bluish stars. But the light from these seeming stars told a bizarre story. Their spectra were shifted so far into the red that it was staggering. This immense redshift meant these objects were not stars at all. They were the most distant things ever observed, billions of light years away, receding from us at a significant fraction of the speed of light. The puzzle was their brilliance. To be visible across such a cosmic gulf, a single quasar had to outshine an entire galaxy of hundreds of billions of stars. Yet this titanic energy was pouring out from a region smaller than our own solar system. What kind of cosmic engine could possibly be that small, that powerful, and that efficient? The only conceivable power source was a supermassive black hole, millions or even billions of times the mass of our sun. A quasar is the active, screaming core of a young galaxy, where a voracious black hole is feeding. As colossal amounts of gas, dust, and even stars spiral into the accretion disk surrounding the black hole, the material is compressed and heated to millions of degrees, blazing with light before it crosses the event horizon and vanishes. The incredible pressure and magnetic fields can also funnel some of this infalling matter into twin jets that shoot out from the poles at nearly the speed of light, carving across intergalactic space for millions of light years. The discovery of quasars forced a dramatic rewrite of cosmic history. They revealed that the early universe was not a placid place of slowly forming galaxies. It was a chaotic, violent arena where galaxies were born in a frenzy of activity, their central black holes feasting on the abundant gas of youth. This frenetic energy actually helped shape the galaxies themselves, regulating star formation and influencing their ultimate size and structure. We now understand that most large galaxies, including our own Milky Way, went through a quasar phase in their distant past. Our galactic center hosts a quiet, dormant giant, a relic of that ferocious early era. Quasars are the cosmic lighthouses of the deep past, their intense beams illuminating a time of dramatic creation and destruction, showing us that the seeds of today's majestic galaxies were sown in the furious hearts of the universe's most powerful engines. That same cosmic web of galaxies revealed by the Hubble Deep Field is not a static tapestry. It is a river in motion, and our entire galactic neighborhood is caught in its current. For decades, astronomers mapping the motion of the Milky Way through space found something deeply unsettling. Our galaxy, along with our entire local group, is not just drifting aimlessly. We are racing toward a specific, mysterious point in the sky, located in the direction of the constellation Centaurus, at a staggering speed of over 2 million kilometers per hour. The source of this immense pull was named the Great Attractor. The problem was, when we looked toward that part of the sky, we could not see it. Our view was blocked by the dense stars and gas of the Milky Way's own galactic plane, a region astronomers call the zone of avoidance. It was like trying to find the source of a mighty river's current while standing in a thick, obscuring fog. The initial discovery was a profound puzzle. What invisible force could possess enough gravity to tug on thousands of galaxies, including our own, with such irresistible strength? The answer did not lie in a single, monstrous object. As observing techniques improved, allowing us to peer through the galactic dust with infrared and radio telescopes, we began to see the true scale of the structure. The Great Attractor is not a thing, but a place, a gravitational focal point. It is the core of the Laniakea supercluster, a vast filament of over 100,000 galaxies to which our Milky Way belongs. This supercluster spans an almost unimaginable 500 million light years. The gravitational heart of Laniakea is a massive concentration of galaxies known as the Norma cluster. But even its immense visible mass was not enough to account for the observed pull. The true engine of this cosmic motion is dark matter. The Great Attractor is, in essence, a mountain of dark matter, an enormous overdensity in the cosmic web, whose invisible gravitational field dictates the motion of everything within its sphere of influence. This discovery fundamentally changed our understanding of the universe's structure. It showed us that galaxies are not randomly scattered. They are organized into continent-sized superclusters, and these vast structures are themselves in motion, flowing along invisible rivers of dark matter toward the densest nodes in the cosmic web. Our journey toward the Great Attractor is a silent testament to the overwhelming power of the unseen, a constant reminder that even on the grandest scales, the ghostly hand of dark matter is guiding the cosmic dance. Our journey toward the Great Attractor maps the cosmic large scale, but a similar gravitational pull has reshaped our own celestial backyard. For centuries, our solar system appeared to end with Pluto, a lone sentinel in the dark. But the story was never that simple. In the 1950s, Dutch astronomer Jan Uwit was trying to solve a cosmic mystery. Where did the long-period comets, those spectacular icy visitors that take thousands or even millions of years to orbit the Sun, actually come from? He proposed a stunning solution: a vast, spherical shell of icy remnants surrounding our solar system far beyond the known planets. This theoretical Uwit cloud, he suggested, was a cosmic deep freeze, a reservoir of trillions of icy bodies stretching nearly halfway to the next star. Its gravitational hold is so weak that a passing star, a gentle nudge from the galaxy itself, can dislodge one of these primordial fossils, sending it on a long fall inward toward the Sun, where it blossoms into the comet we see. Around the same time, astronomer Gerard Kuiper proposed a different, closer reservoir. He suggested a disc-shaped region of icy worlds just beyond Neptune, a belt of leftover building blocks from the solar system's formation. For decades, these were just elegant theories, the ghostly outlines of a larger solar system we could not yet see. The proof began to emerge in the 1990s. With powerful new telescopes and sensitive digital cameras, astronomers began a meticulous survey of the outer darkness. What they found was a revolution. They discovered a whole new class of world, small, icy bodies orbiting the Sun in the realm beyond Neptune. The first major find was a body named Albion in 1992. The floodgates were open. We had found the Kuiper belt. This was not a sparse, empty zone. It was a teeming ring of frozen debris, a cosmic junkyard holding thousands of known objects and potentially hundreds of thousands more waiting to be found. This discovery instantly reshaped our solar system. Pluto was not a lonely oddball. It was the king of this belt, the largest known member of a vast new population. Our planetary system was not 8 or 9 planets with empty space between them. It was a dynamic, structured place with a clear architecture, featuring an inner zone of rocky planets, a middle zone of gas giants, and now a confirmed outer zone of icy worlds. These frozen bodies are more than just comet sources. They are pristine time capsules, preserved in the deep cold of the outer solar system for 4.5 billion years. By studying them, we are looking at the original ingredients that went into making our planets, a fossil record of our own creation. The discovery of the Kuiper belt and the theoretical framework of the Uwit cloud revealed that our home in space is not a small, tidy system, but a sprawling domain whose farthest reaches still brush against the interstellar void. Even the air we breathe carries invisible messengers from deep space. At the turn of the 20th century, physicists were puzzled by a persistent background radiation that seemed to come from everywhere. They initially thought it was a minor leakage from the Earth itself, but a series of daring experiments revealed the truth was far more extraordinary. In the 1910s, Austrian physicist Victor Hess took sensitive electrometers high into the atmosphere aboard hydrogen balloons, risking the frigid, thin air at altitudes exceeding 5,000 meters. He discovered that the radiation did not decrease with height, as it should if it were terrestrial. Instead, it intensified dramatically. The source of this mysterious ionizing radiation was not our planet, but the cosmos itself. Hess had discovered cosmic rays. We now know these are not rays at all, but a torrent of high-energy atomic nuclei, protons and electrons, racing across the galaxy at nearly the speed of light. They are the shrapnel from the universe's most violent events, accelerated by forces we are only beginning to understand. A single one of these particles can carry the energy of a professionally thrown baseball, all compressed into a subatomic speck. When they slam into our upper atmosphere, they create spectacular cascades of secondary particles, a silent, invisible rain that passes through our bodies and the Earth every second of every day. The true mystery lies in their origin. What cosmic engines can possibly hurl matter with such ferocious energy? We have traced some to the shock waves of supernova remnants, where expanding shells of debris act as natural particle accelerators, far more powerful than our largest human-built colliders. Others appear to come from more exotic sources, like active galactic nuclei or colliding galaxies, events of almost unimaginable power. These relentless particles are more than just a curiosity. They are a continuous sampling of the distant universe, providing a direct physical connection to processes we could never otherwise touch. They have revealed the nuclear furnaces inside stars, the explosive death of massive suns, and the turbulent magnetic fields that weave through interstellar space. Every time a cosmic ray streaks through the atmosphere, it carries a tiny piece of a stellar cataclysm, a silent witness to the fact that we live not in a quiet, separate cosmos, but within a dynamic and sometimes violent galaxy that is constantly reaching out to touch us. That silent rain of cosmic particles is a reminder of the universe's violent present, but to understand its full story, we needed to find its birthday. For most of human history, the age of the cosmos was a matter of pure speculation, a philosophical debate with no data to constrain it. The breakthrough began with the discovery of the expanding universe. If space is stretching, then running the film backward in time implies a moment of beginning. The rate of that expansion, known as the Hubble constant, became the universe's ultimate clock. By measuring how fast galaxies are receding from us and how far away they are, astronomers could calculate how long ago they were all squeezed together. But this was fiendishly difficult. Pinpointing the true distances to far-off galaxies required ingenious methods and painstaking work, leading to decades of debate and refinement. The initial estimates were wildly uncertain, suggesting an age somewhere between 10 and 20 billion years. This created a profound crisis when it was compared to the estimated ages of the oldest stars in our own galaxy. For a time, it seemed some stars were older than the universe itself, a logical impossibility that pointed to a serious flaw in our models. The solution came from an unexpected direction, the same faint whisper that started it all. The cosmic microwave background radiation, mapped with exquisite precision by satellites like WMAP and Planck, provided a completely independent way to read the cosmic clock. The specific pattern of hot and cold spots in that ancient light acts like a cosmic barcode, encoding the universe's vital statistics. When scientists decoded it, they found a number that settled the debate once and for all. The universe is 13.8 billion years old. This figure was then cross-checked against other methods, including vastly improved measurements of the Hubble constant and detailed studies of the ancient, metal-poor stars in the Milky Way's halo. All these independent lines of evidence now converge on the same answer. This is not just a number. It is the foundation of our cosmic timeline. It tells us that everything we see, from the farthest quasar to the closest star, has unfolded within this finite span. It places the formation of the first stars a few 100 million years after the Big Bang, the assembly of galaxies like our own around 9 to 10 billion years ago, and the birth of our solar system a mere 4.5 billion years in the past. We are living in a mature universe, one that has had ample time to forge the elements, build the galaxies, and set the stage for life. This precise age is a fundamental pillar of modern cosmology, a single number that anchors our entire history and forces our theories to account for a universe that is both ancient and dynamic. 13.8 billion years is the age of our entire observable cosmos, a vast expanse containing 2 trillion galaxies. Yet the most profound question remains unanswered. Why does this universe have the specific set of physical laws and constants that allow for our existence? Tweak the force of gravity by a fraction, or adjust the strength that holds atomic nuclei together, and stars would never form, chemistry would be impossible, and life could not arise. This perfect, seemingly fine-tuned balance has led to a staggering idea, one that emerges directly from our most successful theories. Our universe may not be the only one. The concept of a multiverse has shifted from science fiction into a serious, though speculative, scientific framework. It arises from 2 powerful pillars of modern physics. The first is cosmic inflation, that frantic expansion of the primordial universe. Many versions of inflation theories suggest that once this process begins, it never truly stops. Instead, the fabric of spacetime can undergo eternal inflation, with new bubble universes continually budding off from the inflating background. Each of these bubbles could have its own unique local laws of physics, a different set of constants frozen into place as that bubble forms and cools. In this view, our entire cosmos is just one bubble in a frothing, infinite sea of other universes. The second pillar comes from string theory, an attempt to unify all forces and particles. String theory allows for a colossal number of possible stable configurations, often estimated to be 10 to the power of 500. Each configuration corresponds to a universe with a different set of physical laws. If this is correct, then the reason we find ourselves in a universe suited for life is not because it is special, but simply because we are here to observe it. In an infinite multiverse, every possible universe must exist somewhere. This idea fundamentally challenges the Copernican principle, the notion that we do not occupy a privileged place in the cosmos. On the scale of our universe, that still holds true, but on the scale of the multiverse, it implies our entire cosmic history, from the Big Bang to today, is just one ordinary iteration in an infinite ensemble. We are living in a universe that is utterly average and unremarkable, a single tree in an endless forest. While we may never have direct observational evidence for other universes, the multiverse hypothesis forces us to confront the very nature of reality. Is our cosmos a unique, singular creation? Or is it just one page in an infinite book of cosmic possibilities, where other versions of you might be pondering this very same question under a different set of stars? Deep beneath the Earth's surface, in the quiet darkness of a mine, scientists were counting ghosts from the sun. For decades, we had understood the nuclear furnace at the sun's core, the process that creates the light and warmth that sustains all life. Our models were precise, predicting that countless subatomic particles called neutrinos should be streaming out from those fusion reactions and passing through our planet every second. These particles are phantoms, so ethereal they can fly through light years of solid lead without a single interaction. To catch even a handful, physicists built incredibly sensitive detectors in abandoned gold mines and deep tunnels, shielded from cosmic rays by a mountain of rock. But when they started counting, the numbers made no sense. The detectors were finding only about 1/3 of the neutrinos our best physics said should be there. This was the solar neutrino problem, a glaring mismatch between theory and observation that persisted for 30 years. Was our model of the sun wrong? Were our detectors broken? The answer, when it finally came, was far more strange and wonderful. The neutrinos were not missing, they were changing. On their 8-minute journey from the sun's core to our detectors, these ghostly particles were shape-shifting. The sun only produces one type, the electron neutrino, but by the time they reached Earth, some had transformed into two other known varieties, the muon and tau neutrinos. The early detectors could only see the electron type, rendering the others invisible. This phenomenon, called neutrino oscillation, was a monumental discovery. It meant that neutrinos, long thought to be massless phantoms that always travel at the speed of light, must have a tiny but real mass. According to the bedrock rules of the standard model of particle physics, a massless particle cannot change its identity. The simple act of oscillation proved they weigh something, however infinitesimally small. This was not a minor adjustment. It was the first clear, experimental crack in the seemingly complete edifice of the standard model, forcing physicists to rewrite their textbooks. These elusive particles, once thought to be mere cosmic spectators, were now revealed as active players with a secret identity and a whisper of mass, fundamentally altering our understanding of the most fundamental building blocks of everything that exists. The faint, steady ticking of pulsars and the silent rain of cosmic rays are the background hum of a mostly peaceful galaxy, but the universe has a far more violent and explosive side. In the late 1960s, American military satellites designed to monitor for secret nuclear weapons tests began picking up brief, intense flashes of radiation. They were not coming from Earth or even from our solar system. These were gamma-ray bursts, and they were the single most powerful explosions in the cosmos since the Big Bang itself. For decades, their origin was one of astronomy's greatest mysteries. They appeared at random from any point in the sky, flashed with unimaginable ferocity for a few seconds, and then vanished forever, leaving no trace. The energy released in those few seconds was staggering, often outpacing the total energy our sun will emit over its entire 10 billion-year lifetime. What kind of cosmic catastrophe could possibly be this brief, this bright, and this powerful? The mystery began to unravel when powerful telescopes managed to capture the faint, fading afterglow of these bursts. They pinpointed the sources to incredibly distant galaxies, billions of light years away. To be visible across such a mind-numbing gulf, the explosion had to be of almost inconceivable power. We now know there are two primary cosmic engines behind these flashes of pure fury. The longer bursts, lasting more than 2 seconds, are thought to be birth cries of black holes. When a truly massive star, dozens of times heavier than our sun, reaches the end of its life, its core collapses not into a neutron star, but directly into a black hole. The infalling material can form a swirling accretion disk, and from the poles of this system, jets of plasma are launched at over 99.99% of the speed of light. If one of those ultra-focused jets happens to be pointed directly at Earth, we see it as a long gamma-ray burst. a final, spectacular scream from a dying star in a hypernova. The shorter bursts, lasting less than 2 seconds, are even more dramatic. They are the death spirals of the densest objects in the universe. When two neutron stars, or a neutron star and a black hole, finally merge after circling each other for eons, they create a cataclysm of almost biblical proportions. In the final milliseconds before they collide, they rip each other apart, flinging out material that glows with the light of a billion suns, and forging heavy elements like gold and platinum in a cosmic forge. The merger creates a new black hole, and again, if we are in the path of the jet, we witness a short gamma-ray burst. These fleeting flashes are more than just cosmic fireworks. They are the universe's most powerful beacons, illuminating the process of creation and destruction on the grandest scale. They are the crucibles where the gold in your jewelry was likely forged, a violent and beautiful reminder that even in the darkest corners of space, the end of one thing is often the beginning of another. Those fleeting, violent gamma-ray bursts are but tiny sparks against an unimaginably vast cosmic architecture. For a long time, our maps of the universe showed galaxies scattered like isolated islands in a dark sea. But as our surveys grew more ambitious, a breathtaking pattern began to emerge, a structure so immense it defies human comprehension. We now know that galaxies are not randomly distributed. Instead, they are woven into a cosmic web, a colossal filamentary structure that spans the entire observable universe. This web is made of long, twisting strands of dark matter, upon which galaxies are strung like pearls on an invisible string. These filaments connect at dense nodes, where thousands of galaxies swarm together in massive clusters, and they surround vast, empty regions known as cosmic voids, bubbles of near-nothingness that can stretch for hundreds of millions of light years. How did we ever map such a grand design? The key was the Large Redshift Survey. By meticulously measuring the redshifts of hundreds of thousands of galaxies, astronomers could plot their positions not just on a flat sky, but in three-dimensional space, revealing their true distances from us. Projects like the Sloan Digital Sky Survey painstakingly cataloged the night sky, and when all those points were plotted, the result was stunning. The map revealed the web in all its glory, a lacy, interconnected network of staggering scale and beauty. This vast architecture is the direct descendant of those tiny temperature fluctuations we see in the cosmic microwave background. Those minute ripples were the seeds of all structure. Over billions of years, gravity acted as a cosmic sculptor. The slightly denser regions, where dark matter was more concentrated, began to pull in more and more material from their surroundings. Ordinary matter, the gas and dust that would become galaxies, was funneled along these invisible dark matter highways, flowing into the gravitational wells. The filaments grew thicker, the clusters grew denser, and the voids expanded as they were drained of their material. The cosmic web we observe today is the mature, fully evolved version of that primordial blueprint. It is the largest pattern in nature, a direct link between the quantum fuzz of the infant universe and the majestic, galaxy-filled tapestry we see now. This structure is not static. It is a dynamic, flowing system, with galaxies steadily migrating along the dark matter filaments toward the great clusters at the intersections, in a slow, cosmic river that has been flowing for over 13 billion years. To see this web is to finally understand our true address. We do not just live in the Milky Way galaxy. We live within the local group, which resides on the outskirts of the Laniakea supercluster, which is itself just one thread in this single, magnificent, and unbelievably vast cosmic web. The surface of Mars today is a frozen desert, a seemingly barren landscape of rust-colored dust and rock. Yet etched into that dry skin are the unmistakable scars of a watery past. For centuries, we saw the red planet as a dead world, a cautionary tale of a planet that had dried up and died. But a series of robotic explorers, our mechanical proxies on that distant soil, have completely rewritten that story. From orbit, satellites have captured breathtaking images of vast, dried-up riverbeds, sprawling deltas where water once met a standing body, and deep canyons that could only have been carved by catastrophic floods. These are not subtle features. They are the geological ghosts of a planet that was once drenched. The Mars Reconnaissance Orbiter, with its powerful cameras, has even identified specific minerals, like clays and sulfates, that can only form in the presence of persistent liquid water. This orbital evidence painted a picture of a young Mars with a thicker atmosphere, a warmer climate, and lakes, rivers, and perhaps even a vast northern ocean. The real confirmation, however, came from the ground. Rovers like Curiosity have been trundling across the Martian landscape, acting as robotic field geologists. They have driven directly into ancient lake beds, analyzing the mudstone and finding it rich with the very same minerals that form at the bottom of lakes on Earth. They have examined rounded pebbles, smoothed by a long-vanished river's current, and seen sedimentary layers deposited slowly over millennia in calm, standing water. This is not the story of a brief, catastrophic flood. It is the story of a world that was wet and stable for a very long time, perhaps for millions of years. And the water is not all gone. Orbiting radars have peered beneath the surface at the polar ice caps, revealing that they are not just made of frozen carbon dioxide, but contain enormous volumes of water ice. Vast glaciers of pure water ice lie buried just under the dust in the mid-latitudes. We now know Mars holds significant reservoirs of water, frozen in its soil and at its poles. This cumulative evidence has fundamentally transformed our quest. Mars is no longer just a dead rock to be studied. It is a once habitable world, a planet that met all the basic conditions for life as we know it for a substantial period of its history. It had liquid water, the essential solvent for biochemistry. It had all the necessary chemical elements. It had an energy source. The search has therefore shifted. We are no longer just looking for water. We are looking for the fossils of that ancient wet era, for the chemical signatures that life, had it ever arisen, would have left behind. Every new rover we send is a paleontologist, digging into the rocks of a world that once whispered with the promise of life, searching for an answer to one of humanity's oldest questions. Are we alone, or was Mars, too, once a living world? That search for life's building blocks on Mars is a quest to understand our own cosmic rarity, but to truly grasp why matter exists at all, we had to journey into the emptiest space imaginable, the quantum void. For decades, the standard model of particle physics stood as a triumphant but incomplete masterpiece. It perfectly described the menagerie of subatomic particles and the forces that govern them, with one glaring exception. The equations demanded that particles like electrons and quarks be utterly massless, forever racing at the speed of light. Yet we know they have mass because without it, atoms could never form, and neither stars nor people would exist. Something had to be breaking the perfect symmetry of the early universe, something that gave substance to the ghostly quantum fields. In 1964, physicist Peter Higgs and others proposed an elegant, almost magical solution. They suggested that all of space is permeated by an invisible field, now called the Higgs field, Imagine walking through an empty room. You move freely. Now imagine that same room filled with a dense, invisible crowd. Your movement becomes sluggish. You require more effort to push through. This is the Higgs mechanism. As elementary particles move through the cosmos, they interact with this omnipresent Higgs field. Some particles, like photons, slip through without any interaction, remaining massless. Others, like electrons and quarks, drag through this field, and this interaction is what we experience as their mass. The more a particle interacts, the heavier it is. The theory predicted that if this field was real, it should have a fundamental, vibrating manifestation, a particle known as the Higgs boson. Finding this particle became the single greatest challenge in modern physics. It required recreating the unimaginable energies of the universe's first trillionth of a second. The quest culminated deep underground, in a 27-kilometer circular tunnel straddling the French-Swiss border. The Large Hadron Collider is the most complex machine ever built, designed to smash protons together at velocities infinitely close to the speed of light. For years, it collected data from billions upon billions of these microscopic collisions, sifting through the debris for a specific, fleeting signature. Then, on July 4, 2012, the announcement echoed around the world. Two independent teams at the LHC confirmed they had found it. They had discovered the Higgs boson. This was not just the discovery of another particle. It was the discovery of the mechanism that fills the universe with substance. It confirmed the existence of the Higgs field, the cosmic molasses that gives mass to the fundamental building blocks of reality. This completed the Standard Model, but its implications reach far beyond the atomic scale. The Higgs field is thought to have undergone a dramatic phase transition in the universe's first moments, a shift that fundamentally altered the properties of empty space and set the stage for the formation of all matter. It provides a profound bridge between the quantum world of the infinitesimally small and the cosmic scale of the entire universe, explaining how a featureless, symmetric fireball cooled into a structured cosmos capable of building galaxies, planets, and us. The Higgs boson is more than a particle. It is the key that unlocked the final door to our current understanding of why the physical world has the substance and structure that it does. Deep in the silent expanse beyond the planets, two robotic explorers were drifting toward the stars, but they carried a secret. The Pioneer 10 and Pioneer 11 spacecraft, after completing their historic missions to Jupiter and Saturn, were now coasting into the interstellar void. Yet as scientists tracked their precise trajectories, a tiny, persistent anomaly emerged. The probes were slowing down slightly more than they should have been. An unknown force was exerting a feeble but constant tug back toward the sun. A deceleration so small it was like a single snowflake landing on a moving car. But over years and years of travel, it added up to a navigational mystery. For decades, this pioneer anomaly baffled physicists. Was it the gravitational pull of some unseen, nearby dark matter? Could it be a hint that our understanding of gravity itself, Einstein's general relativity, needed a slight adjustment in the vast, empty scales of the outer solar system? The anomaly became a tantalizing ghost in the machine, a whisper that perhaps we were on the verge of discovering entirely new physics. The solution, when it finally came, was a lesson in humility and ingenuity. A team of researchers dove into the old engineering documents, even recovering decades-old data from magnetic tapes. They painstakingly built a thermal model of the aging spacecraft. They realized that the nuclear power sources on board were constantly emitting heat. This heat, radiating from the spacecraft's body, was bouncing off the large dish antenna at the back. Every time a photon of heat radiation bounced off that antenna, it gave Pioneer a tiny, tiny push back toward the sun. It was not a dramatic new force of nature, but the cumulative effect of countless minuscule photons, a gentle photon breeze that had been slowing the probes all along. This explanation accounted for almost the entire anomalous drift. The mystery was solved not by rewriting the laws of physics, but by appreciating the profound subtlety of engineering. Yet its legacy is profound. The decades-long hunt for the cause forced us to measure the motions of distant spacecraft with unbelievable precision, creating a new standard for navigating the solar system. It demonstrated that even the most tantalizing clues for new physics must first survive the rigorous test of known physics, and that the universe often hides its most profound truths not in the grand explosions, but in the quiet, patient accumulation of tiny, almost imperceptible effects. What other subtle whispers are we missing in the data from our other deep space travelers? Whispers that might still be waiting to reveal a deeper layer of reality. A single, startling signal pierced the cosmic silence, and for 72 seconds, it felt like a message. On a hot August night in 1977, astronomer Jerry Amon was reviewing data printouts from Ohio State University's Big Ear radio telescope, a sprawling array tasked with scanning the sky for narrowband radio waves. His eyes scanned the columns of letters and numbers, a monotonous record of cosmic noise, until he saw a sequence so extraordinary he circled it in red pen and wrote one word beside it: wow. The signal was not a natural cosmic phenomenon. It was a powerful, focused burst at exactly the frequency of the hydrogen line, a universal marker scientists had long predicted an advanced civilization might use to announce its presence. It came from a seemingly empty patch of sky near the constellation Sagittarius, rose to an incredible intensity, and then faded away exactly as expected for a signal from a fixed point in space, drifting through the telescope's stationary beam. It had all the hallmarks of a deliberate, artificial transmission from beyond our solar system. The search for an earthly explanation began immediately. Was it a secret military transmission, a reflection from a passing satellite, or some bizarre equipment malfunction? Every possibility was investigated and systematically ruled out. The Big Ear telescope had 2 separate feed horns, and a signal from Earth or a nearby satellite would have appeared in both. The WOW signal was detected by only one horn, confirming its origin was firmly in deep space. For decades, astronomers have returned to that same spot, using more powerful instruments, listening for a repeat for anything. The silence has been absolute. The signal never returned. This singular, unrepeated event remains the most tantalizing and frustrating clue in the search for extraterrestrial intelligence. It stands as a ghost in the machine, a one-word testament to the profound possibility that we are not alone, and a stark reminder of the immense, needle-in-a-haystack challenge of listening to a galaxy that may be shouting, but only once. The WOW signal remains a haunting, unanswered question, a brief flicker of possibility in an otherwise silent cosmos. But while we listen for signs of other life, our telescopes have managed to do something even more profound. They have begun to look back to a time before any stars or galaxies existed, to an era of absolute blackness known as the Cosmic Dark Ages. For billions of years after the Big Bang, the universe was a vast, featureless expanse of hydrogen and helium gas, a fog without a single source of light. Then, slowly, gravity began to pull the densest patches of this primordial gas together. The first stars ignited. these were not like the stars we know today. They were behemoths, hundreds of times more massive than our sun, and they burned with a ferocious, pure blue intensity. They lived fast and died young, exploding in cataclysmic supernovae that seeded the cosmos with the first heavy elements, the carbon, oxygen, and iron that would one day become the building blocks of planets and life. For years, this cosmic dawn was purely theoretical, a chapter in our universe's story we could model but never see. Then the Hubble Space Telescope began pushing its vision to the limit, finding faint red smudges of light from galaxies so distant we were seeing them as they were just 400 million years after the Big Bang. But Hubble was seeing the outlines of the story. We needed an instrument that could read the text. The James Webb Space Telescope, with its infrared eyes, was built for this exact purpose. It is a time machine designed to peer through the dust of time and capture the light from those very first stellar nurseries. Its initial images have already upended our expectations. The early universe is not the sedate, slowly forming place we once imagined. It is a riot of activity, filled with fully formed, bright galaxies that emerged far sooner than any model predicted. We are witnessing the universe's infancy, a period of frantic construction where the first structures were being woven into the cosmic web. This is the final piece of the timeline, the direct observation of creation's first act. By studying this cosmic dawn, we complete the circle, connecting the quantum seeds in the ancient afterglow to the majestic galaxies that now fill the darkness. We are no longer just theorizing about the beginning. We are watching it happen. These 25 discoveries have completely rewired our perception of reality. We began this journey with the comforting, static universe of our ancestors, a small stage with Earth at its center. We now know we live in a cosmos dominated by invisible forces, where dark energy relentlessly pushes space apart and dark matter, a ghostly presence we cannot see, provides the hidden scaffolding for everything. Our universe had a violent beginning, underwent a frantic inflationary growth spurt, and is now home to trillions of galaxies, each one a potential archipelago of worlds. We have learned to listen to the ripples in space-time from colliding black holes and to look back in time to see the first stars ignite. From the quantum seeds in the ancient afterglow to the vast cosmic web, every discovery has peeled back a layer, revealing a universe that is far stranger, more dynamic, and more interconnected than we ever dreamed. We are not merely inhabitants of a small planet. We are conscious stardust, born from the explosions of ancient suns, living in a universe that is evolving, expanding, and filled with mysteries we are only beginning to grasp. This cosmic perspective is the true legacy of these revelations. So we turn the question to you: which of these 25 discoveries most fundamentally changed your view of existence? Was it the shocking acceleration of dark energy, the ghostly pull of dark matter, or the first direct image of a black hole's shadow? Share your thoughts in the comments below, and subscribe to continue this journey of cosmic revelation.